All right, thanks for being here, guys. Again, if you have any questions, feel free to either unmute yourself and you can feel free to ask your question, or you can just write in the Zoom chat box. Either way is fine. Okay, so I'm just going to do a little bit of, let me see here. Okay, just a little bit of what's upcoming, and also want to kind of highlight a couple of important things on the class announcements page. So I'm trying to put everything into this under this AP review schedule and reminder. Again, if you haven't gone through the AP exam, the AP exam demo, definitely take some time to do that. You want to make sure that whatever method you're using, that you're comfortable, and that worst comes to worst, that you're submitting 5 pages within 5 minutes. So see if you're able to do that consistently for problems 1 and 2. The exam demo is not going to be the length of your exam. Your exam demo is going to, the exam demo is only going through 10 minutes. So first 5 minutes, you're just kind of waiting until the last 5 minutes to start uploading. But on the exam is going to be 30 minutes and 20 minutes. Okay, so don't think that what you're seeing on a demo is going to be the length of the exam. It's going to be a lot longer. Okay. I also moved the resources up to 9B. So I think these are good resources for you guys to print out. So the fall summary, the spring summary sheet, integral derivative rules, reference sheet, College Board's AP exam checklist, and then also tips and advice, which we're going to go over today. Okay. I advise you guys to take time and go through the summary sheet and rules with a highlighter, just so that you have what you feel like you find helpful to be highlighted. Okay. So I'm going to be going over mock exam 1 and 2 tomorrow, and then also 3 and 4. These are just extra credit mock exam problems that some of you guys may be doing. So I moved the link up from the bottom of the page to the top here. So if you want to do it alongside me as we go through the review session, then you can just take the work that you did and just turn that in. You can do that as well, or you can work it through beforehand. I'm going to try to work it in real time, but we'll see. I don't know exactly if I can do all this within the time frame, but we can kind of play it by ear. And then on Monday, the day before your exam, you're going to be, I'll go over the big 4 FRQ topics. So, and then if we have time, I added more review in case you guys want to do it. But I don't know if I'll have time maybe to go through all of this, but if you have specific questions over these, I'm going to try to make videos for each of these. But if you have specific questions, I'd be happy to go through as well. So, these may be more than what you're willing to do, which is fine. I just want to have resources out there in case any of you want to do additional problems. Okay, so there's no grades for these two, so just kind of gives me something to go over with you guys, and gives you some additional practice if you choose to use it. You should have received emails from College Board, and then by Sunday, you should be getting an e-ticket for this AP Calculus exam. So on Monday, I think I'm going to send out a text reminder, just making sure, if you've received the e-ticket, then that's great. But if you haven't, or if you're having trouble finding it on your My AP, I'm going to ask you to contact me, and we'll see what we can do from there. But you should be having access to your e-ticket by the latest Monday, but hopefully Sunday before your AP exam. I think these are also good resources for you guys to print out. So weeks 4 through 6, these are the FRQs that you guys did. I think these are good to also print out as well, and also good to look over as well, right? Look over these. Maybe you want to highlight some of the problems or concepts that you see within these. I think, these are the ones with the highest chances of showing up. So I think these are good resources to print out as well, the FRQs that you guys did for weeks 4 through 6. Right, so these are the summary sheets that is on, that I highlighted under resources. So, the fall and the spring, I think these are good for you to kind of go through and make sure that everything is fresh in your mind in terms of all the concepts, the steps, and you might want to put a highlighter to it just to kind of highlight the things that you feel are important, okay? And then you can cross off anything dealing with chapter 7 and 8, so integration by parts, tab method. So we didn't get to these points, and this method and washer method is not going to be on the exam, so you can cross these out. Okay. Okay. I don't think I want to kind of go over screenshots again. I know I'm doing a lot of things before I get to the tips and advice, but I guess it's also part of it as well. When you're practicing, I feel like these are good recommendations that I would follow. Is they say you can use number 2 pencil or pen. I would choose pen with black ink just because it's easier to show up on paper. And sometimes with pencil, if the lighting is not great, then it may not show up as well. So I prefer that that you use pen with black ink. Now, if you feel more comfortable with pencil, that's fine. You just have to make sure that when you take a picture that you're making extra, that you're double checking that that whatever picture you're taking, that everything is showing up nicely. But I think pen with black ink is going to be the safest in terms of being legible and easy to read. So take your photo in a well-lit space. Try not to have any shadows on your paper. Take your photo overhead with camera above. Take your photo straight on, not at an angle. And then, double check your photos, right? Double check that your photos are clear. I mean, I'm sure that, there's so many ways that things can go wrong. I mean, it'll be unfortunate, but I'm sure it's going to happen where, students put all this work and they think they did well, but then what happened was that their photo was unclear, right? If their photo is unclear, then they're not going to be able to give you a score because you didn't. They can't read your work. So double check that your photos are clear. I have a link for if you want to do PDFs in the front, but I just feel like I'm getting some conflicting information from College Board. So I just feel it's safer to do JPEG files, take photos one by one, and then and upload each of them individually. And I don't think you should have to do more than 2 or 3 pages, so it shouldn't take that long. But ultimately, it's up to you. I just feel like JPEGs are going to be more straightforward than PDFs. And then make sure it's JPEG, PNG, or JPG, not HEIC. So just make sure that when you go through your demo, that you're double checking and making sure that the file extension that's coming up is JPEG. All right, so I'm going to start going over the AP testing tips and advice. So this is under, if you want to print this out and go through along with me, this is this link here under 9F. And then I also have an addendum with tips and advice. So I'm going to kind of pull up some of these concept examples for some of the points that I'm going to be highlighting. So you can, print this out as well. I recorded 2 videos for these, and I'm also recording this session as well. So if you want to look through or if you want to review the video that I did, you can do that as well. So I'll make that available. Okay, so first thing here is just want to go through some definition and descriptions of common AP terms and advice. So whenever you see a function is twice differentiable, this shows up a lot at the beginning of FRQs. So just understand that twice differentiable, all it is trying to tell you is that it's a smooth curve, that it's not going to be anything strange with sharp turns. So you really don't have to do anything with this statement. Just understand that it's a smooth curve with a degree that's at least x squared. So maybe x cubed, maybe x to the fourth, but just understand that, you know, it's just a smooth curve, all right? And that the second derivative value is at least a constant. It's not going to be zero. So there's not going to be a straight line or a horizontal line or a graph with like absolute value function, okay? All right, so something that that is nice and smooth. Differentiable function, this just means a smooth curve, no sharp turns. Derivative or slope is going to exist at every point on the graph. Differential equation, this is an equation that is in the derivative form. So anything that has y prime or dy dx with an equal sign, if this dy dx equals 3 minus y times x, that's a differential equation. And when it says solve the differential equation, that means we want to be able to bring this up from a derivative to the original function level. So we practice a lot with chapter 6 where we separate the variables, cross multiply, take the antiderivative of both sides. So hopefully we've done enough of these practice where you're comfortable or getting comfortable with it. Finding equation of a tangent line. So you're going to see this quite a bit as well. And this is where you're going to first gather information about the line. So you need to find order pair, which they'll at least give you the x value. If they don't give you the x and y value, then you can take the x value, put it into the original function, and get that order pair. And then to find the slope, you just plug into the derivative function or the derivative differential equation to get that slope. Once you get your order pair and your slope, you put into point slope form. Okay. And then to find, when it says find dy dx, that just means find the derivative equation or the derivative formula. I want to point this out here. Let uppercase h of x be the antiderivative of f. So whenever you see the statement, you have to understand that they're trying to, the problem is trying to show you that there's a relationship between this uppercase h and this lowercase f. And here's the relationship. The relationship is that the antiderivative, h is the antiderivative of f. What that's saying is f is really at the derivative level of h. Okay, so this is just the way that College Board is going to phrase it if they're just wanting to say that, you know, the f is really just h prime. Okay, right, so the f is just the h prime graph. Let's see. Okay, so this is an example that is on that addendum sheet here. So I want to kind of show you kind of that application for this. So, well, actually, let me get back to this when I go over second fundamental theorem. So, yeah, okay, so I'll come back to this, but this is something that's related here. Okay, any questions so far? All right, again, I'm just kind of going through these terms and phrases that pops up a lot on AP exams, especially on free response questions. Find the absolute max, absolute min. Whenever you see this, that should be an indication that, all right, they're trying to get you to identify steps for extreme value theorem. So that means you need to find the critical points. You need to somehow set f prime equal to 0, either algebraically or from a graph. Then you're going to be identifying your endpoints. So once you identify endpoints and critical points, you're going to put them all into the original function, and then see which one produces the absolute max and absolute min. Okay. Find the instantaneous rate of change. So instantaneous rate of change means find the exact rate of change, and that means we need to find the derivative at a point. So if you're given the position function, then you find the derivative, which is velocity, and then plug whatever the x value is, let's say, or the t value, v of 5, that will give you the instantaneous rate of change of that particle or that object at that moment in time. Find the average rate of change. Now, average rate of change, if you're given the position function, you're not going to find the derivative. You're not going to get to the velocity. So what you're going to do is you're going to think of this as average velocity. So average rate of change, we don't use the velocity function. We do change in position over change in time. So we're just finding slope between the two endpoints using position function. Okay. All right, next one down, related rates. You know you're dealing with related rates when you have time involved in the problem, and what you're going to do is you're going to be finding the derivative, or you're going to be creating d over dt for each variable. So, for instance, find the rate at which the area of the circle is changing at that time, or the beach ball is deflating at a rate of 10 cubic centimeters per second. So these are all kind of key phrases, key terms that should kind of hint you to the fact that it's going to be a related rates problem. So let me just kind of give some quick examples of what you would do once you get to that point. So with related rates, and this is off of the addendum sheet here. With related rates, you're always going to be creating some sort of an equation, whether it's algebraic or trig or geometric. And you're always starting with an equation, and then from there, you're going to find the derivative. And each variable is going to have its own d over dt. So x squared, you find the derivative using power rule, but then as soon as you do that, you're going to attach a d over dt for every variable, because the hidden independent variable is time. Okay. For this one here, for tangent theta equals y over 20, we can also find the derivative for related rates here. So tangent theta, the derivative will be secant squared, and then theta will have its own d theta dt. Y over 20 is same thing as 1 over 20th times y. So if I want to find the derivative of 1 over 20th times y, the 1 over 20th stays. Y becomes 1, but then we attach dy dt. Okay. And if I want to find the derivative for related rates, if I'm starting with volume of a sphere, then 4/3 pi stays. It's a coefficient. R cubed becomes 3r squared, and then we attach dr dt. All right. So every variable produces a d over dt. Remember, pi is not a variable, so there's no d pi dt. Okay. So. All right, this statement here for number 12, at what time does the instantaneous velocity equal the average velocity over the given time interval? Or sometimes a problem could say, at what time does the instantaneous rate of change equal to the average rate of change? So whenever you see this connection between instantaneous rate of change and average rate of change, that should be a red flag that this problem is trying to get you to apply mean value theorem. Okay, so mean value theorem, instantaneous velocity, instantaneous rate of change, that's the derivative. We set the derivative equal to the slope between the endpoints because that's what mean value theorem guarantees. It guarantees that whatever slope you find between the endpoints, we can guarantee that specific slope is going to sit somewhere on that curve. Okay. All right, so I'm going to show a couple of examples once I get into mean value theorem rolls on the next page. This statement here, use the data in the table to approximate the rate at which the temperature is changing. So you see the word approximation. So whenever you're approximating a rate, that means you're not going to be using derivative. You're going to be using slope, okay? Because slope is an approximation and it's not going to give you the exact value. So what you're going to do is you're going to take the two closest order pairs, closest to whatever point that they're asking you for you to approximate. And then you just do change in y over change in x, or change in temperature over change in time. This notation, d2y over dx2, that just means find the second derivative. Okay. First theorem of calculus application. Final position equals initial position plus displacement. F of b equals f of a plus the definite integral from a to b of f prime. So let me go through this first theorem application. It showed up on a couple of mock exams, but I want to go through an example with you, and it's also on the addendum, so you can look at it more closely if you don't have that in front of you. You can print that out later. So here is what that first theorem application is. We've done this with a couple of problems. Our final position equals initial position plus displacement. So let's say we have an example where you're given the velocity function. And let's say the values are provided inside these regions. So let's say this is displacement of 3, this is a displacement of -7. Let's say the areas are already found, but we adjusted the signs with positive and negative. And the problem says, given that the position at x equals -1 is 5, find the position at -4. So we want to be able to use the velocity to help us get from one position to the next. So we're going to use this formula, right? So the position that I'm looking for is x of -4, so I'm going to replace b with -4. The position location that I'm given is this x of -1, which is 5, but right now I'm just going to put x of -1. And I'm always going to start at my initial point and end at my final point. So they may be out of order, but you're always going to make sure that your lower bound is going to match with whatever number is here. So -1, -1. I'm going to end at -4, because that's my final position. Okay. So now once we set this up, we can then take a step back and say, wait, is this out of order? If it is, then I can always adjust it. So I see that it is out of order because I want to be able to read this graph in a straightforward way from left to right. So I'm going to flip the bounds. And once I flip the bounds, I'm going to change the sign from positive to negative. So now x of -1 is just equal to 5. The definite integral from -4 to -1, I just look at the graph here. That's showing me a +3. And then once I put that 3 there, I'm going to carry that negative through. So 5 minus 3 equals 2. You may see different variations of first theorem, this application. F of b equals f of a plus definite integral from a to b of f prime. Or you may see something where everything is moved down 1 degree. So it could work for this as well. My final velocity is equal to my initial velocity plus the displacement of my acceleration. So we can, a problem could ask you to apply it in this form as well. Okay. All right, any questions? All right. Okay, item 15 here. When you approximate value using Riemann sums, which is area approximation using rectangles, either left, right, even trapezoid rule, I would consider that as an approximation of area. Your units of measure is going to change. Okay, so keep that in mind. If the values in the table are in terms of gallons per hour, then after Riemann sums, if it says explain what the units represent, we have to understand that it's no longer going to be gallons per hour, right? We accumulated all those rates, then it's going to it's going to move up 1 degree from gallons per hour to just total gallons, right? So keep that in mind, that whenever you push anything through Riemann sums, your units will change, right? Let's see, be able to recognize when the problem wants you to apply certain theorems. So sometimes you're asked to apply first theorem. So let's say you don't have, let's say you have a table of values, but the table of values is not W prime, it's W of t. Well, how can we connect from W prime with something that we can use with the table, we can push this through first theorem, right? Take the antiderivative. W prime will turn into W of t, and then we plug in our upper and lower bounds. So sometimes this could be the way that we arrive at the location where we need to be in order to use the table. Second theorem, this is really highlighting, hold on, did I? Okay, I think, yeah, I'm going to go through this in more detail in a second, but basically second theorem is kind of a shortcut method, and it also highlights the fact that derivative and integrals, if you apply both operations on top of one another, it's going to leave this function kind of untouched with a few slight adjustments. The upper bound does get plugged into the expression, and the upper bound's derivative is also being multiplied. Okay, product rule, quotient rule. A lot of times they like to insert these problems or parts into FRQs. If limits are involved, consider the possibility that you may have to involve, maybe it's trying to get you to go through continuity conditions, or maybe it's a L'Hopital's rule problem where you got to find the derivative of the numerator and denominator and reevaluate. So if you see limits involved, it's usually one of these two. These are the most common concepts that can show up. Okay, chain rule. Chain rule is where we have to identify outside function and inside function and take turns with each of their derivatives. So let me go through an extended one here. This is one that has 3 different layers. Sometimes the trig functions can do that. So if I have cosine cubed with 4x, what you want to do is first you want to rewrite this. Okay, this is not as easy to interpret. You want to put that 3 outside a set of brackets. And then you'll have an easier time identifying all the parts needed for chain rule. So there's a outside, there's the inside, and there's the inner. Now the chain rule here is only showing an outside and inside, but this is an extended one where we have to go through 3 separate steps to build our derivative. So why don't I do this problem with you guys. So let's say we have y is equal to cosine of 4x, quantity cubed. There's an outside portion, which is the bracket cube. There's the inside, which is the cosine of parentheses. And then there's the most inner function, which is 4x. So if I want to find the derivative, we have to step through each of the different layers to produce the derivative. So first is bracket cube. Think of bracket as just its own variable. So we do power rule there. So we get 3 bracket squared. That will take care of the outer function's derivative. So now we're going to move on to the next part, which is cosine of parentheses. Cosine parentheses, cosine's derivative is negative sine. So this becomes negative sine of parentheses times the innermost function's derivative. And 4x's derivative is just 4. Now, what goes inside the bracket is going to be, we're just going to carry that down from what we see above. And then what goes inside the parentheses, we're just going to carry that down from here. So we can clean this up a little bit and make the coefficient and the negative push out in front. Okay, so this is a kind of extended problem with chain rule. Okay. And then I think there's a couple of ones that we're going to apply using function notation, and I'll go over that on the mock exam. It shows up on a couple of mock exams, so I'll go over that tomorrow and Sunday. All right, next statement here. If a problem asks you to find a horizontal tangent line, what you're going to do is you're going to take the derivative, and you're only going to set the numerator equal to 0. Whatever causes the numerator to be 0, is where your horizontal tangent line is going to be. If the problem is asking you to find the vertical tangent line, you're going to locate the derivative function, set the denominator of the derivative equal to 0, and that will help you find that. Okay, so I think I have an example of that here. Yeah, so let's say I have my derivative equation being 3x minus 6 over 4y plus 2, and the problem says find the horizontal tangent for this graph. So you're going to set the numerator equal to 0, solve for x, and when you solve for x, in this case x equals 2, so you know there's a horizontal tangent on the original f of x graph at x equals 2. And there's also a vertical tangent, because that is whatever causes the denominator to be 0. So slope undefined is going to be is wherever 4y plus 2 is equal to 0, which is y is equal to negative 1/2. So when y is equal to negative 1/2, on the graph, there's going to be a vertical tangent. So I'm just kind of showing you an example of the concept that that I highlighted. Okay, number 18, linear approximation. I think a couple of these problems may have shown up on the mock exam as well. Local linearization, linear approximation. I know this sounds complex, but really you're just doing one additional step after your tangent line equation. So we talked about tangent line equation, right? Tangent line equation, you're going to find your slope using your derivative. You're going to find your order pair, and then you're going to put it in the point slope form. All right, so that's half the battle there. If you can find that tangent line equation, then your linear approximation is you're just plugging that decimal in for the x and solving for y. Okay, so don't let this combination of words throw you off, right? You're just start with what you know, build that tangent line equation, and then once you have your tangent line equation, you're just going to find that decimal value, put that decimal value that they give you, whether it's 0.1 or 2.6 or 5.9, in for the x, and then you can use your calculator to find that estimation. All right, so I have a couple of these examples on the mock exam. We can go over that. On FRQs, they like to insert different concepts. So the popular ones are IVT, EVT, mean value theorem, Rolle's. These kind of go hand in hand a little bit. These are kind of connected. L'Hopital's rule, first theorem of calculus, second derivative test. Okay, this may be a little bit less common, but I want to go over that. Related rates, sometimes they like to stick related rates into parts of the problem as well. So let me go through each of these big theorem names here. So the first one is IVT. Let's see, did I have an example of IVT? Okay, so IVT, there's no calculus involved with IVT. It's just kind of, it just makes sense if you just think about it. So IVT says, so the function is continuous, right? That means there are no breaks in the graph. Then the graph is going to reach all the y values between my endpoints. So if I start at a y value of -3 and I end up at a y value of 5, then we can guarantee that the graph is going to cross through a y value of 1 or a y value of 2, because it has to connect through that y value somewhere in between. Okay, so here's an example of IVT here. This is off of the addendum sheet. It says, for instance, what's the least number of times that a y value can be equal to 3 in the given interval? So it's been established that this function is differentiable, and if it's differentiable, you know it's continuous as well. So IVT says, well, it's going to have to cross through as many times as we see graph that dips above and below that target y value. So if we're trying to go through target that y value of 3, we start at -4. From -4 to 5, it has to cross through a y value of 3 at least once. 5 to 2, it's going to have to cross through a y value of 3 at least once. 2 to 5, it's going to have to cross through a y value of 3. But then from 5 to 10 and 10 to 20, we don't have, the graph may completely avoid 3. It may not dip down, right? But between these points, it has to cross through 3, has to cross through 3, has to cross through 3. So by IVT, we can guarantee that by IVT, it's going to reach a y value of 3 at least 3 times. Okay, so if you just kind of visualize the graph, you can convince yourself, okay, it has to cross through at least once through that interval. Okay, extreme value theorem. I think we talked about this. If a function is continuous on a closed interval, then we can find the absolute max and absolute min by just simply considering and testing the endpoints and the relative max and relative min. All right, if you look at a graph that is connected, the only places that we have to consider for highest and lowest points are endpoints and critical points. Critical points is wherever my derivative is 0 or wherever my derivative is undefined. And derivative undefined is where f, the denominator of f prime, is equal to 0. Okay, these don't happen as much. I feel like the ones that you're going to see are probably just going to be wherever f prime is 0 and wherever your endpoints are. So these are the only points you have to test, okay, to find the absolute max or absolute min. Okay, mean value theorem and Rolle's. Let me go through these again. So mean value theorem says if a function is continuous and differentiable, so connected curve and smooth curve, we can guarantee a specific slope of the tangent line by finding the slope between the endpoints. So whatever slope exists between the endpoints, we can guarantee that slope to sit somewhere on the curve itself. So here's an example of mean value theorem drawn out. So let's say we have endpoints A and B, and you have the order pair, you have the function, and you plugged in to find the y value, and you have the x value, so you do change in y over change in x, and you found that the slope is equal to 2. Now, whatever slope of this line is, it could be 2, it could be 1/2, it could be 3. Whatever that number is, that is the slope that mean value theorem is going to be able to guarantee. We can, let's say this is equal to 2. This slope is 2. Then we know for sure that there must be a location where a slope of 2 is going to be reached by the curve at least once. And what mean value theorem does, it allows us to find a location on the curve where that specific steepness is occurring. So we set f prime, the derivative equation equal to the slope between the endpoints, and when we solve for x, we're able to locate that specific location on the curve where that behavior occurs. So mean value theorem is trying to guarantee that specific slope value on the curve, and that slope value has to exist between the endpoints, provided that we've already gone through the conditions, connected and smooth curve. Now, sometimes you may see an adapted form of mean value theorem. It's not just for f prime for connecting between the slope between the endpoints of the original function and the derivative. We can move everything 1 degree down, and it could also apply as mean value theorem. So what I mean by that is we can also guarantee a g double prime value by finding the slope between the endpoints of the derivative. So basically, I'm just moving all of my function notation down 1 degree. So f prime goes to f double prime. My endpoints is now for my endpoints for my derivative function. So just be aware that sometimes mean value theorem can still be applied even if you're not dealing with a function and the derivative. It could be the derivative and the second derivative. Okay, that could also hold true. All right, now something that's related is Rolle's theorem. Rolle's theorem is just a subset of mean value theorem. But it's also trying to guarantee a slope, but the slope that it's trying to guarantee is very specific. It's not just whatever slope is between the endpoints. Mean value theorem can be a slope of 3, it could be 3/2, it could be 2/3. But Rolle's theorem, it has to be a slope of 0. But if we want to guarantee a slope of 0, we need an additional restriction. And that restriction is the endpoints have to be directly across from each other. It must be at the same y value. That's the only way we can guarantee a slope of 0 without looking at the graph. So the conditions are the same. We still need a connected graph. We still need a smooth curve. Okay, sorry if my internet, I said my internet was unstable, so I'm sorry if I was cutting out there. So here, Rolle's theorem does apply because the graph is continuous, it's differentiable, and notice my endpoints are the same height at the same y value. Because I can draw a horizontal line between the endpoints, I can therefore guarantee a slope of 0. So Rolle's theorem has an additional condition. The endpoints have to be the same y value, but once it's the same, then if you find a slope between the endpoints and the two y values are the same, we can guarantee that slope is going to be 0. And then we just set our derivative equal to 0, and then we find that location, we find that c value, okay, where that slope occurs. Now, Rolle's theorem can also be adapted. It doesn't have to be between the function and the derivative. It could be between the first derivative and the second derivative. Okay, if g prime of a equals g prime of b, if the endpoints of my derivative graph have the same y value or same slope, then I can guarantee a location where g double prime is equal to 0. Right? So I'm just really taking Rolle's theorem and just adapting it 1 degree down. Let's see. Okay, first theorem of calculus. I think we went over this, but I'm going to go over an example with you guys. First theorem of calculus says I can take the antiderivative of a function and make it become the antiderivative. So lowercase f becomes uppercase f, or we can have f prime turn into f of x, or we can have f double prime turn into f prime. Okay, so first theorem, you're just kind of moving whatever level that function is, and you're moving it 1 degree up. Okay, so there's one specific example I want to go over with you. Because I want to show you that sometimes the notation can look so similar, but the process that you go through is completely different. Okay, so I want to see if you can follow along with this example that I want to do with you here. All right, let's say we have W prime given, and W prime represents the rate at which waste is being added to the landfill. So in year 1, we have 30 tons per year, okay? And then year 3, it's increasing at 40 tons per year, okay, so on and so forth, right? So these numbers, it doesn't represent how much waste is in the landfill. It's just telling us the rate at which it's filling the landfill. So part A says approximate the definite integral from 1 to 10 of W prime. Now we have W prime in front of us. So what we can do is, if we're trying to find the integral of W prime, we can just find the area under this W prime and be able to reach our conclusion. But it's going to be using left Riemann sums, which is an approximation method. So this we've seen and we've done, right? We create the regions, we find the width between the endpoints of our t-value. So 4 minus 1 is 3, 7 minus 4 is 3, 10 minus 7 is 3. And then once we have the width components, we also want to find the height. We want to choose the height that is on the left side. So 3 times 30, that's the left subinterval height. 3 times 50, and then width times height, 3 times 35. And then we get to 345. Now notice how W prime starts off as tons per year, but once we push it through Riemann sums, the units are going to change because this is no longer going to be a number that represents tons per year. This is now going to be representing the tons of waste in the amount. So my units is going to suddenly change from tons per year to tons of waste accumulated over the course of those 9 years. Okay, now this doesn't mean that there's 345 tons of waste sitting in the landfill. It just tells us that this is how much have gained in the landfill from year 1 to year 10. Right? If we want to figure out how much is in the landfill, we still have to add on whatever was existing up to that point, or up to that time. So here, right, the integral from 1 to 10 of w prime, we're applying Riemann sums, but I want to show you what we do here with this next example. Now here in the table of values, let's say I don't give you w prime, I gave you the actual amount in terms of the waste. So let's say year 1, there's 1,400 tons. Year 3, there's 1,490 tons in the landfill. Okay, we see it going up, but it's a different unit. Now, let's say I ask you to find the same thing in terms of notation. What's the definite integral from 1 to 10 of w prime? Now here, we don't have w prime, so we're not going to find the area, right? We're not going to find the area under with w prime because we don't have w prime in front of us. So we need another method, right? How do we get from w prime to w of t so that we can actually use these values? So here, we're not going to do Riemann sums. We're going to make it go through first theorem. So we're going to find a way to convert this w prime to w of t so we can actually use these values. And first theorem says, well, if we make that w prime go up a level, we can make it go from w prime to w of t. And then first theorem says, well, once you push it through the integral process, you can plug in the upper and lower bound. So once this w prime pushes through integral, we make it w of t, and then we plug in the upper and lower bound. So w of 10 minus w of 1. So that's 1750 minus 1400. So we get 350. Now, 350 is not an approximation. It's also the same units as what we did before, but this was an approximation, and we use a different method. This is an exact value. Okay, it still represents the same thing. It still represents the amount of waste that's accumulated or changed between the first and the 10th year. But notice how A and B is showing the exact notation in terms of what it's asking for, but the method that we're applying is completely different based off of the information that's provided. So just be careful. Sometimes definite integral may be asking you to do Riemann sums, but other times it's maybe asking you to go through first theorem and then just subtracting certain values. So I want to point this out because it's such a subtle thing, but it's an important distinction. Okay, any questions with that? Okay, so I have this printout if you want to look at this more closely. So I have it under today's section here. So wait, where did it go here? Yeah, so addendum and the tips and advice. So this is what I'm going through here. Okay, this is more of a potentially a minor topic, but I want to kind of go over it just in case it shows up. This is called the second derivative test. I know that this is misinterpreted as finding points of inflection using the second derivative sign line, but it's not. Okay, second derivative test is using the second derivative function to find max and mins. So let me read through this definition, and then I'll show in a specific example. So let's say we find the critical point to be slope 0. So we know that's a potential point for relative max, relative min. Normally, you would just maybe go through your slope sign line and then see if there's a change in rise to fall. And if there is, you know there's a relative max. But we're going to use a different method here. We're going to be determining max and mins not by using the sign line, but using the second derivative function. So what we're going to do is we're going to take that critical point that we've already determined to be a slope 0, and we're going to plug it into the second derivative function. And if it gives us information that it's part of a concave up graph, which is a positive number, that means it's concave up, that means it's a relative minimum. Okay. So we're using a different method rather than using a slope sign line to determine the relative max, relative min. And likewise, if I take that critical point and plug it into the second derivative function, and if I get a negative value, let's say -5 or -8 or -10, that means the graph is part of a concave down graph. If it's part of a concave down graph, then that point must be part of a relative max. Okay, let me show you an example of that. Right, so let's say this is what the problem gives you. It says that a function is differentiable, smooth curve, order pair at 3, 4, and a slope of 0. Now, if it just gives you order pair and slope of 0, you have an idea, but you don't know exactly what's happening here, right? Maybe it's a graph that is where it's neither a max nor a min, right? It just levels off. Or it could be part of a relative max, all right? Or it could be part of a relative min. But just from where we have, right, these all fulfill conditions of slope 0. So now the next step that we can take is, rather than using a sign line, let's say we plug that 3 into the second derivative function, and in return we get a positive 6. Okay. From these two information alone, we can conclude what type of a relative extrema is happening here. Now 6 is a positive value, and if 6 is a positive value for a second derivative, that's going to correspond to concave up. And if you can visualize what concave up looks like, and the fact that it's a slope 0, then we can conclude that there must be a relative min at x equals 3. So that's what second derivative test is doing. It's using the second derivative function to determine the same thing that we would otherwise do if we did the first derivative test. Okay, but sometimes a problem forces you to use the second derivative test, especially if they don't give you any information about the function, which makes it difficult for you to use the first derivative test. Okay, likewise, let's say that critical point that we found, plug into the second derivative function, and we get in return a negative value. If we get a negative value, then we can correspond a negative second derivative value with concave down. All right, so concave down looks like this. If we pair that with the fact that it's a slope 0, then we can conclude that point must be a relative max. Okay. And then finally, if the second derivative function gives you also 0, then it just tells you that it's inconclusive, that this is not a good way for us to, we can't make a conclusion based off of this, because it could end up being a relative max, relative min, or neither. But I don't think you're going to see, I mean, if they're asking you to apply second derivative test, they're not, I don't think they're going to go through this point, because it's not really showing the AP test makers whether you fully understand it. So if they're going to give it to you on the test, it's going to probably fall into these two categories. All right, let's see here. All right, let's next point here. Oh, related rates. I'm kind of backtracking here. I talked about this already, but if time is involved, just more examples. Let's say find the rate in which person is walking, find the rate of change of the surface area. Balloon is rising at 4 feet per second. Bike A is going at 2 meters per second. So all these are kind of key phrases, key terms to kind of hint you to the fact that, okay, there's probably going to be related rates going on, which means I need to find the derivative. I got to produce d over dt all over the place, and then fill in my values to find my missing variable. Okay, I inserted a bunch of related rates problem on mock exam 3, so we can look over that on Sunday. A couple of points here. Just because my slope is 0, it doesn't mean that we can guarantee a relative max or relative min, right? You got to make sure you go through your slope sign line and justify with words. And this is the more problematic thing, is sometimes students, they see a second derivative value go to 0 and they assume, okay, that must be a point of inflection. Okay? It's a critical point, but we can't guarantee point of inflection until we actually go through a concavity sign line. So let me show you an example of that. Right, just because my f prime is equal to 0, it could be a place where the slope may not be a relative max, relative min. Okay, so this I think we're comfortable with. This, sometimes we run into some trouble just assuming that, okay, if my second derivative is 0, then it must be point of inflection. But we see that's not the case here, right? If there's no change in sign, that's not a point of inflection. Right? There has to be a change in sign in order for us to call that the point of inflection. Okay, only at D, not at C. Couple more points here. These may be more minor, but I want to kind of make sure I go through these. if a problem asks you to find the derivative of a log or natural log expression, such as something as messy as this, you don't want to jump into the derivative. Okay, you want to spend the time to expand the expression, and then you can do your u prime over u. Okay, so let me show you an example here. Okay, so I'll go through this quickly because you can kind of go through this on your own thing, but we want to take advantage of log properties, right? So I have this whole mess. I don't want to go through a series of quotient, chain, and product rule. So I'm going to try to split everything up. So I can expand this out. I can think of this as A, B over C. So anything in the numerator, I can put a plus in between. Anything in the denominator, I can put a minus in between. So now we're able to kind of conquer and divide, right? We're able to, or sorry, divide and conquer, split everything up into individual terms. And then we'll have a much easier time with the derivative. And we can continue expanding, bringing the exponents down in front. And now we have 3 easy problems to do: u prime over u, u prime over u, u prime over u, and that's our derivative. Okay. Item number 23. Okay. If a problem involves an exponential function of a variable raised to a variable, let's say something that looks like this, x raised to the 1 minus x squared, we don't have a rule available that can find the derivative in this form. So what we're going to do is we're going to take advantage of log differentiation. We're going to force this into a log problem so that we can bring that exponent down in front. Okay, so the steps that you're going to take, you'll take the natural log of both sides. Okay, expand the right side using log properties, product rule on the right side, and then implicit differentiation. So let me go through the steps here. We see that we don't have a rule for a variable raised to a variable. We take the natural log of both sides. Oh, sorry, let me answer the question that Ryan posed here. Which practice exam will we be covering in tomorrow's session? It's going to be mock AP or mock exam number 1 and number 2, and it's under the extra credits. So some of you may have already done that already. Okay. And I also have that link here. So let me just show you real quick. On my AP schedule here, I have a practice test 1 and 2. So if you have time, go through these. Okay. And if you want to do this with me tomorrow, then you can just submit it to me as extra credit. Okay. So you can either do it beforehand or you can do it with me tomorrow. But yeah, I'll be going over that tomorrow. Okay. So take natural log of both sides. We can bring that exponent down in front. And then notice that this is product rule, so f prime g plus fg prime. Natural log of y, we have to go through implicit. This becomes 1 over y dy dx. Move the y over to the right side, and then replace the y back in terms of x. Okay, chances are pretty low this is going to show up, but I just want to go through with it, in case this shows up. And if it does, then you've gone through an example, and you can quickly figure out what to do. All right, last few points here. Include units with your answer only. It's only needed if the problem asks for it, but maybe it's safe just to include it. But yeah, they're not going to take out points if they don't ask for units. No need to simplify answers. Okay, so point slope form, leave it in that form, and then. But I don't think, because there's no non-calculator portion, so this may not happen. But yeah, just keep in mind, once you have a numerically equivalent answer to your final simplified answer, then just leave it. Okay, you don't need to simplify it. Okay, just be clear with what you're try to avoid. It is increasing, or that those words can be unclear, and the grader may not know exactly what you're talking about. In your calculator, make sure you're in radian mode and not in degree mode. This is steps for clearing calculator in case your calculator just all of a sudden you don't know what you pressed and you can't get back to what you want to see. You can go to second memory, 712, and that will clear the memory and bring you back to your normal form. But I think, yeah, just double check though when you do this that go to mode and make sure that you're still in radian mode. All right, I want to go over this last item here. So last 2 years, I got a chance to do grading for FRQs. And this was an eye-opening thing to see. I don't necessarily agree with this, but this is how they do things sometimes. And I want to point this out, just in case, just, I guess just the more you know, that it could benefit you. Oh, actually, there is something I want to go over before I go over this, and that is with L'Hopital's rule. Now, this is something, it kind of, yeah. So I was watching a video or a webinar with some of the teachers who have led some of the grading experiences at Kansas City when I went for grading, and this is something that. Yeah, so let me talk about this and talk about what it is that they need to be aware of. And I'll repeat this as well over the course of the next few days. And here's the thing, sorry, I'm getting, okay. Here's the thing, with L'Hopital's rule, I've always kept saying, hey, if you just find the limit, if you get 0 over 0, then you can push it through L'Hopital's rule, right? I've used that notation over and over again. And I think the book uses it as well. But some of these college board teachers, they are not so keen about this. They don't like this 0 over 0. And the reason why is because, this is just because when we plug 8 in, is it really fully representing, it doesn't represent every instance of 0 over 0. And so this is a little problematic in terms of notation. So here's a safe way to do it. Maybe they're going to decide that this is not a big deal and they're not going to take off points. But here's a safe way to do it just in case. Okay. So the safe way to do it without having to use this 0 over 0, which I've been doing, and I think a lot of teachers do it as well. The safe way to do it is take the evaluate the limit separately. So do the limit of the numerator. So let's say my g of 8 is equal to 1 and g prime of 8 is equal to 0. So let's say that's given to you. And I'm going through my limit. I plug in, I get g of 8 minus 1, 1 minus 1 is 0. Okay, obviously the numerator is 0. Okay. And then separately, I'm going to do my limit expression for my limit for my denominator. So I'm going to put 8 into my denominator here, and I'm going to get 63 minus 64 plus 1, which is 0. Okay, so I have 0 over 0, but I'm not going to write 0 over 0. I'm just going to write my two limit expressions separately, and then I'm just going to move directly to say, okay, by L'Hopital's rule. So I'm going to avoid writing this out. Okay, I've justified that I'm going to do L'Hopital's rule because the numerator is 0 and denominator is 0, but I'm not showing a 0 over 0. And now I'm going to go through my L'Hopital steps. So take the derivative of the numerator. G becomes G prime, 1 goes to 0. Derivative of the denominator, 63 goes to 0. X squared becomes 2x. E to the u becomes e to the u times u prime. Plug 8 into my resulting derivative expression. And then whatever number I get is my answer, right? That's a real number, so that's my answer. So I want to point this out because some of them are not happy about writing it in this form. So yeah, this is the safe way to do it. Okay, so I'll remind us of this because I think on my keys I'm showing 0 over 0, and I just watched this recently, and so I'll probably go back and re-highlight that. But at worst, they'll take off a point. Right, that's the worst case scenario. But just in case. Okay, here's the last thing I want to go over with you. This is something that I did not know about, okay, until I went to the grading experience. And this is frustrating as a grader because I'm going through a specific test, and students, I see their work and everything looks great, except they do a linkage error. And because of that, I got to take off a point, and it's frustrating to see. But here's what it is. Let's see. Can you use the table question to show right Riemann sum? Okay, yeah, I'll do that after I go through this. Okay, but yeah, I'll answer your question. So here's what linkage error is. It is where, you know how sometimes we use equal signs just to kind of show that we're progressing from one part to the next. We really don't mean that they're equal. We're just showing, you know, maybe as a student, you want to let the teacher know, okay, here's my next step, so equal to. So this is where they don't like that. So let's say your definite integral is 1 to 4 is equal to 6. Find, and the problem says, find the definite integral from 1 to 3 of integral from 1 to 4 of f of x. And so I say, okay, this is equal to 6 because this I substitute with 6, and then I'm going to bring the 1/3 into it. So 1/3. So in the end, my answer is correct, right? This is equal to 2. But along the way, there's an error, right? This is a linkage error because 1/3 times 6 is not equal to 6. So sometimes they ask graders to take off a point here because that's called a linkage error. And that's frustrating because, you know, like, all right, I know that students don't really mean that, but they're just kind of progressing along. So you have two options. If you want to avoid linkage error, you know, just write down each of your steps, but don't put anything in between, right? You can just make it logical so that the graders will know, okay, this is my first step, then my second step, my third step. Don't put equals all over the place, okay? Especially when you're connecting two different pieces of work, right? Sometimes we as graders have to take off a point because there's something here, and all of a sudden it just has like a faint equal sign here. And we got to take off a point because that's a linkage error. So one way to avoid it is don't put any equal sign between your work, especially when if there's, you know, all sorts of different disconnected pieces of work. And the second is use arrows. If you use arrows, then they're more forgiving. They say, okay, well that arrow just shows the student is not really saying they're equal, just saying, okay, this is my next progression in my step. So this, I'm showing that, okay, I'm doing portion of this, which is 6, and then I'm going to eventually lead to an answer of 2. So they define linkage issue as a solution presented using equal sign to connect expressions that are not equal. So two ways around it: use arrows, or just don't use any don't use anything in between, and just use you know, just go from one step to the next without indicating anything between it. Okay. Let's see. Okay, so I think what the table, this one here. Okay, this one here. Okay, using right Riemann sums. Okay. Sorry, I'm getting a sheet of paper here. So my width is all 3. But the height is going to be different. So width of 3, my height, this is my left, that's my middle, that's my right. So 3 times 50. And then second interval has a width of 3, a height of 35. And then the last interval has a width of 3 and a height of 15. Okay, so that's Riemann sums for right Riemann sums. Okay. Sometimes a problem may say, is this going to be an under approximation or over approximation? So let's say that this problem is, okay, we see that's not the case. Well, let's say this graph is always increasing. Okay, so that's always increasing. let's say we're doing right Riemann sum, always increasing. Is it going to be an under approximation or over approximation? Then what we can do is give yourself a visual, create a graph that's always increasing, and then the right Riemann sum, that means we're attaching the right endpoint to represent the height of each rectangle. Right Riemann sum in this case is going to be an over approximation because we have portions that's going to stick above. So that's something that I think I have it on a couple of the mock exams where, you know, the graph is always increasing or decreasing. Sometimes they'll ask, okay, if it's left Riemann sum or right Riemann sum, is it going to be an under approximation or over approximation? So the best way to do it is just to draw the graph out and convince yourself whether those rectangles are sitting nicely below the curve or do we have portions that stick above it. If it's above, then we know it's over approximation. If everything is under the graph, then we can call it an under approximation. Okay. Let's see, let me just double check. Did I go through everything I want to go through with you? All right, guys, thanks for being here. Just a couple of last things here. Tomorrow, I'll go over mock AP exams 1 and 2. These are under these. Some of you guys may have already done this. This is the extra credit at the bottom of the page. And then on Sunday, I'm doing a little bit earlier at 3 p.m. And if you don't show up to these sessions, you can watch the video, or I'm going to record these Zoom sessions and I'll put it up. And I'll put a link next to these so that you can watch it. And then I have some last minute FRQs as well. Okay. But if you have any questions that I didn't answer, feel free to ask me now, or you can ask me over the text, over chat, or ask me over Remind. But I want you guys to feel comfortable going into the exam. Yeah, that's all I have for you guys. Again, if you haven't done the AP exam demo, or if you only done it once, maybe you want to do it a couple of times to just make sure that you can get everything under that 5-minute window. Okay. All right. Thanks, everyone.
Thank you, Mr. Yang.
Yeah, see you, Caitlin. If you have any questions, I'll stick around in case you want to ask me anything.